Good afternoon, colleagues and students. Thanks for coming to our seminar. Today, it gives me a pleasure to welcome Gcina Maziya, the doctor, who is my postdoc, and is going to talk to us about the COS method. This is some sort of numerical method for pricing options. And it's going to look at pricing these exotic options that are called barrier options. And so as you might know, that there are not closed form solutions, especially under some models like Heston model. So now many people resort to numerical approach, such as Monte Carlo simulation, but Monte Carlo simulation is of course computationally expensive. So Gcina is going to talk to us about this methodology, which is called Fourier cosine method. Gcina, over to you.
Okay, thank you, Messias, for the introduction, and thanks everyone for coming. I'm going to tell you about the cosine method and how it's used to price barrier options, which is one of the options called exotic options. So, excuse me. I mean, the COS method is one of several methods that have been proposed to numerically solve these options because, for instance, in the case of barrier options, there is monitoring which can be done either continuously in time or at discrete times. So what people used to solve this model for the continuous case, like the continuous monitoring in time. And then when they tried to look at the discrete case, but realistically, people were looking at the discrete case, discrete monitoring, and really they couldn't approximate, come from the discretize the continuous case to achieve what is being observed by using the discrete monitoring. So, and then that was a challenge actually, but people started coming up with different ways of doing this. And the COS method, which was recently done by around 2012 by Fang and Ostil, so it's quite recent, and it's one of those methods because we know when it comes to this numerical methods, of course, you can use Monte Carlo simulations, but sometimes we know that it takes a long time to do so. So we want to find another alternative method that are very efficient, computationally efficient, and in doing the job. How do I move here? Sorry. Okay, thanks. So this is the overview. I'm going to introduce some few terms and some definitions, and then we'll look at the derivation of the COS method. Actually, this is the main part that I want to show you. If you can be able to follow the European call options formula, COS formula, because that is what we used in the when it comes to the discrete monitoring of the barrier options, and then I'll show you some numerical results along the way. So there's two parts. The first part is the European options under the Heston stochastic volatility model. Okay, we do Heston here because we know with Black Scholes, the volatility is constant there, and then most people are aware that that is not realistic, and some of the assumptions are realistic. But when you go to Heston, so the Heston came up with this model which is more realistic, so it can predict these things called volatility smiles, for instance. And then so that's why we are interested in this Heston model. So some definitions: an option is a financial instrument whose value depends or derives from underlying variables such as stock indices, currencies, bonds, and so on. There are two main types. So I've mentioned that this is called exotic, which means it doesn't fall. The barrier option doesn't fall under these two. So the normal, what is called the European and then American options. We have a call option and a put option. So a call gives the holder the right to buy an underlying asset by a certain date for a certain price. So you are not obliged to do so, and then you only do it when it's favorable. And then a put option, it gives you the right to sell. And then the terms K is the strike price. We are going to see that, and then many times. And then capital T is the time to maturity. So the value of the option at maturity is a known function. It's given by this for a call. So you take the positive, you only exercise if this is positive. Otherwise, it is 0 and it is weightless. So for a call, if ST is less than K, then you get a 0. So then you won't exercise the option because you are not obliged to do so. So how do we price options? This is one way of doing so called the risk neutral measure way. You discount the expected value of the payoff function. So which is given by this and under the risk neutral measure Q. But what that measure is going to do for us when we look at the evolution of the asset, for instance, the stock price, we'll see that it has a constant trend, and what is going to happen is that that is going to become the same as the risk free rate R. Put call parity. Okay, I'm mentioning this because now sort of to say if you can be able to calculate the call price, then you can use this formula to calculate the put price. So you can calculate one and then use the formula to calculate the add. So depending on which one is of interest or which one is easier to compute, then you can compute one and then get the other one by using this formula. The Heston model, stochastic volatility model. So in the Black Scholes model, here you have a constant sigma where you see the new t there in the second term of DST, the first equation. Instead of that square root nu t, you'll have square root sigma, where sigma is a constant. And once you do that, you have what is called the geometric Brownian motion, and then it means we are under Black Scholes, and then you won't have the second equation because nu will be a constant. So here in this case, the volatility is not a constant. It is a stochastic process as well, as you can see. And then we have the Brownian motions there, the dW1 and the dW2, and then they are correlated via this correlation factor, which is rho. So here are the parameters and definition of the parameters. We are going to skip those. So rho is the correlation, kappa is the speed, theta long-term average volatility, sigma the volatility of the volatility. So sigma is the volatility in the, as we can see in the first volatility nu t. So before we get to the derivation of the cosine method, this is what we need to understand first, or this is what we are going to use in the derivation of the cosine formula. So all the derivations are going to follow from the paper by Fang and Ostelli, because our objective is to replicate the study of this method. So for a function supported on a finite interval 0 to pi, the cosine expansion reads, so you have this f can be written this way in the cosine expansion. So you have the cosine, you have these coefficients are given by this formula. And then if the function is supported on the finite interval AB, then you can make change of variables in this way to get this. And then the function then becomes, in terms of x in the finite interval AB, it can be written like this. And it's a known fact that any function has a cosine expansion when it is finitely supported. So in deriving the pricing formula, we start with this the truncation of the infinite interval range, because we have seen that in the formula where you discount the expectation value of the payoff function, then you have an integral there from minus infinity to infinity, which is over the real line. So we want to approximate that integral. Once we approximate it, so then we get a function that is supported on a finite interval. And then we can expand that function using the cosine expansion, as we can see here. So this is our function that we have again, and then that integral, the last part of the equation, is what we are going to approximate. We'll make it AB. And then we also know that the function f, which is the density function for our process, it decays to 0 quite fast. So then we can have the following. So in the Fourier transform space, we can write the function in this way. So this is the approximation of the function, but this is the actual Fourier transform, which is what we are going to need. So when you integrate in the entire real line. Now using Euler's identity, we get the following: the A case, instead of having the cosine there, you can see that I've used the identity and then the real. I'm taking the real part of that because in that identity, cosine is the real part of E to the power I theta. So I can rewrite the AK instead of using the cosine there, I can write it in this way. And then factoring things out in the second equation. And then in the final equation, we get the approximation of the Fourier transform of that function. So now, instead of the approximation there, which is phi 1, because then we integrate from A to B, we can put back the full Fourier transform. And then we can replace the AK by FK because they approximate each other. So we can use them interchangeably. And then this is what we are going to do. So now our formula, our function can be written in this way. You can see that in that function now we don't have the AKs. We have replaced them by the Fs. So the Fs are given by this. And now the series we have from k equal to 1 to infinity. And then we truncate, we sum from k equal to 1 to n minus 1. So in total, we have n terms. So that is an approximation. And I'd also like you to note that the resulting error, and then in F2, will consist in two parts: a series truncation error and an error originating from the approximation of AK by AF. So this is an approximate result to our original function, but this is what we can work with. So now going back, so we want to derive the COS formula for pricing European options. In order to do that, we go back to our definition of the value of the call or put option. So V is the value of the option at the initial date, T0. So we look today, so capital T is in the future. Tau there is the difference between capital T and T0. So that is the time from now until maturity. So we have our formula there. And then we do what we did when we were discussing how to move from the infinite range R then to a finite range AB. We do the same. We approximate that, and then we get V1, which is approximation of V at T0. So, and then now, so this is another motivation of the COS method, actually, is that if you know the characteristic function, you know that now we have this F, which is the density for the evolution of this stock price or asset price. And then if you know the characteristic function of this density and you don't know, which is most of the time the case, that it's possible to know the characteristic function and then not know the density function itself. So then you will use the cosine method because you don't need to know the density. All you need to know is the characteristic function. So that is another advantage of using the cosine method. So this function now, we are going to write an expansion, cosine series expansion for the density function f, and then the AK become this, and then we substitute the f into this function v1 or v, and then this is what we get because we have done the truncation and then we substituted f there. This is what we obtained. Now in this, if we interchange, we have the sum inside the square bracket there. If we interchange the sum and the integral, we distribute this integral of Vt or of Vyt inside the square brackets. What we are going to get, if we denote Vk by this integral, so what we are going to get is that the first term will get A0 times V0. And then the second one, we have Vk. And then, but that is another a cosine series expansion again for the Vks. So now we get a product of A and V and AK and Vk, which have the same formula. Now we truncate the series again to get the sum from k equal to 1 to n minus 1. And then again, we replace the AK by F. And then when we do that, we get the real part of the Fourier transform or characteristic function. Phi is the characteristic function, which is the Fourier transform basic of a density function is called a characteristic function. So this is what we get. The cosine formula. So we said we don't know the density, we know the characteristic function. So in this formula, you just substitute the characteristic function, and then we calculate the value of the option at time t0. So, but now we need the vks. So we know the characteristic function phi, and then we want to find the vks. We have a formula for the vks. And before we do that, we work in the log with the log of the stock price or the asset price. So we are going to denote x by the log of S0, which is the asset price. I mean the stock price at T0 or asset price. And then Y is ST, that is at maturity. We divide by the strike price, K. And then the payoff function, which we have seen before, where we said we use the maximum of 0, and then this ST minus K, if it's a call option, or K minus ST, if it's a put option. And then it can be written in this way. So instead of ST, you can write ST as E to the power Y times K. I mean, if you look at the second equation, just multiply, take the exponents and multiply by K, and then you will get that payoff function in terms of the log asset price. And then if we do the substitution of VYT into the definition of VK, we are going to get these VKs for this first V is for a call option, and then the second one is for a put option. And then these functions inside there are given by these formulas. So now we have the VKs, right? Because we have this part, we just substitute there, and then we can calculate the value of the option for S0. So these are some numerical results. For the COS method, this is what we get when we set the initial asset price to 80, and if it's 90, 100, 110, and 120. So this is what we get. And then in the paper that we're reviewing by Fang and Ostil, this is the value they got. They calculated it for S not equal to 100. And then they got this value, at least, if I recall well, to two decimal places. So they did get the 5.78 and something, which means the one that is approximate here is for the Monte Carlo method. And these are the parameters that I have used to calculate the values that you see in this table. And then the Monte Carlo simulation, the ensemble size was 10 to the 5. So now the second part, discretely monitored barrier options under the Heston stochastic volatility model. So how do we price discretely monitored barrier options? So, or what are they even? So here you will have the evolution. Normally you will have the evolution of the asset price, and then you look at maturity, and then whether you should exercise the option or not. But here there's an extra condition. So before you even get to maturity, because you'll put a barrier, which I've shown here, we have, so you can see there that at 100, so S on the vertical axis, S equal to 100 is the starting point for those two parts. So that's the evolution of the asset price. But we have a barrier at S equal to 150. So now that sets an extra condition. You want to know at maturity whether you have touched that barrier or not before expiration time. And then so here that capital T is going to be 4 in this case. So we have different 4 types of barrier options. Okay, first we know there's continuously monitored, and then there's discretely monitored ones. So what we want to know is that whether you have touched the barrier or not at maturity. If you touch the barrier, there's knockout, and then there's knock-in. So you can put the barrier below the initial asset price. So this one is an up one. So there's an up and out, which means that if you hit the barrier and then you get out, the option will be worthless before you even go to maturity. So if it's up and in, then it means you have to touch the barrier before maturity. If you don't touch it, then that is going to be worthless. And then the same applies to down. There's down and out, and then down and in. But here we'll be focusing on the up and out. So call options to simplify matters. So here I explained that, okay, in general, this can be written in this way, where you have a rebate of RP, but we'll just set that to equal 0 in our case. So I will consider the case of up and out call options. If you want to calculate put options, then you will have to use the call parity formula. So the cost formula for the option price of this model is given by this formula. So we can see that this is similar to the one we have derived before. The only difference is that you can see that at the end there of this formula, there's a VK at T1. So what is this T1? We're looking at discretely monitored. So we have T0, T1, and then, okay, I forgot to put the T0, which is the initial price. We have T1, T2 up to maturity. So what happens is that we'll use some recursive procedure to start from capital T, and then we move backwards in time until T1. Once we get to T1, we just use this formula is the exact formula like for the European that we have discussed before. So how do we get the VKT1? So that is what I'm going to tell you about to get the VK at T1, because we know how to, we only know the payoff function at capital T. So this is what we need, which is the difference between these discretely monitored barrier options from the European options. So here we have this recursive formula. So we need to calculate this C. So this C, you discount this. So here instead, in the previous case, we had the payoff function at capital T. But now this looks like that discounted expected value as well. So we get the C, and then we kind of like updating this. So the C becomes the payoff function. We know the payoff function at capital T. We go backwards in time. We kind of like calculate what we want to call the payoff function at the T, capital M minus 1, and then so on, up until we reach T1. So in order to do that, so we'll have this VK at time Tm. How do we get that? I will calculate this function that we're going to call CK. And then it's given by this. It's kind of like similar to the previous case. Here we calculate over R, and then we kind of like truncate that integral, and then we can call it capital C. And then we set the C to be equal to the V. And then this is that at maturity we calculate. So this G is actually similar to this, as you can see, but the difference is that G, this is at maturity. So this G actually is the same as V X at T, which is the payoff function that we already know. So that is what we are going to put there. That's the difference between G and C, is that G is when you move from maturity to the next step if you move backwards. So proceeding from there, so at time tm minus 1, we calculate the continuation value, and this given by this, because we know that the payoff function at capital T, which is the Tm, and then the ck. So here, of course, I'm skipping steps. I'm just now showing you what we are going to arrive at. Then we have a prime in the summation, meaning that we will have to include the first term, which is at j equal to 0. Actually, that j should be from 1 to n minus 1, or from 0 to n minus 1. But we know that the first term where j is equal to 0 is not the same as the one as we have seen in the previous summations. And then the m case here are given by this. So what do we get from that? Okay, these are the C case. So things can be summarized in this form. So I think there should be, should I have the K there? Because I have a vector now. Yeah, because if you write things explicitly, then you can reorganize things and then into that. So that should be the same as that one, but I think I shouldn't have that K, because that is the vector of K's, or K from 0 to n minus 1. So I shouldn't have that K, I think. And the V case, because those are vectors, it means the K's are in there. So yes, the V, there shouldn't be that K, that is a typo. In the V and the C, those are vectors. So they are given by this. And then M is the matrix, and then lambda is this diagonal matrix. So yeah, so these two are the same. You can see those are the individual C, C1, C2, all the way to C M minus 1. And then FFT algorithm. So if things are like this way, it's kind of like you have some matrices to multiply. Obviously, they are like n by n matrices, and then that will have this kind of computational time. But things can be rearranged so that an FFT algorithm can be used, which is one of the clever ideas that they came up in that paper, is to say, okay, we can rearrange things, and then they made these observations that these matrices, actually the MC and MS, are well-known matrices like the Toplitz's matrix and the other one, I forget the name now. So in that case, then you can use these clever ways of calculating things. So now you'll have to calculate this product, the product of C and U, and then MS and U, by using this MC, and then with this convolution product of UC, which is given by this. So these D's are the discrete Fourier transforms, and then this is the D inverse, the D to the power of minus 1. And then the definitions for US, UC, MS, and MC, we have them. So we construct the M from, we construct it using these MJs. Okay, so this is an algorithm. So now I've shown you all these parts basic. But if you want to use this method to calculate the option value for this discrete pair option, actually you can just go straight to this algorithm, and then you have everything in place. So you can calculate the V case. We said the objective was this because we already have the formula. So how do we then calculate this until we get a VK at T1? So that is what we want. So we calculate the V case because we calculate the first one, and then we move backwards in time until we get to Vk at time t1. And then for up and out call option, then you set x1 is equal to a and x2 is equal to h. We have seen those in the m's. Construct the m's, and then d1 is going to be the discrete Fourier transform of ms. D2, the discrete Fourier transform of MC. We multiplied by that sign. I think I've made a typo there as well. So that should be MS. So the idea here is that MS and MC are related by this. So that MC in D2 should be MS, because then you calculate it only once, which saves time, because they can be related in this way. So this is the main loop. Here, this is the first things that you calculate. You only calculate these things once, and then you can move on to the loop where you want to calculate until you reach Vk at T1, which is what we want. So you compute the UTs using the U-chase. We have seen the U-chase, they are here. So this is the U. And then you construct US this way. And MSU, you take the first elements, because you have 2n elements actually in that vector. And MCU, you take the first n elements, but then you reverse that vector first, and then you take the first n elements, and then you get your C, which we have seen. You calculate it this way, and then you set your V to be equal to C, and then you repeat this until you get V at T1, and then you want to substitute that V at T1 into this formula. So this is the formula for the option, for the call option in this case at time t is equal to t0. Sorry. So here are some numerical results implemented this method. As you can see, the red means that I didn't get the correct results. So these results are from on the left-hand side, this COS method, the first column and the second column. So those results are from this paper by Chiarella. It's a paper they published in 2012. So they got these results by using the cosine method and then the Monte Carlo. So I did this COS method and then the Monte Carlo, and so I still have to work on this code to achieve the same results. But the Monte Carlo, of course, I did that one, which agrees almost at least to the first decimal place, as we can see with the results in that paper. So the ensemble size was 10 to the power 6. The CPU time for the Monte Carlo is 267 seconds. For the cosine algorithm, it was 0.18. So we can see why, at least in this case, why you would want to do the calculations using the cosine method. For instance, if you have bigger sizes and then things are computationally expensive, then we'll prefer the cosine method from the Monte Carlo simulation. Okay, this is the end of my talk. These are some of the references.
Question, Tina?
Yes, please.
Can you come back to this first table where you are comparing COS and MC?
Mhm.
Okay. Just two things in my mind.
Yeah.
It would be better if you computed the confidence intervals,
Mhm.
say at 90%, and say that our COS method is still because if it gets out of the bounds, then there's something to try about.
Mhm.
Also, the other thing, we are comparing costs with MC. This is not a calculation, it's just pricing. I think we use the sample size of 10 to the half, right?
Yeah.
Perhaps if you want sorting with each value, the MC values changes significantly.
Yeah, that's true, actually.
Pricing
Yeah.
and it's not calculation, maybe it would be better to increase this N, maybe to 10 past 6 or 10 past 6.
Yeah.
That would be more consistent results.
Yes, exactly. I could have done that. I mean, of course, 10 to the power 5 is not because I did it.
That also depends on how complex your model is.
Yeah.
According to what I saw at the end, it's not
Yeah. Yeah, that's true. So they could have increased that, but I just wanted to show that they are close. Of course, if I'm interested in these values, then I can improve by just increasing the assembly size. I mean, it
Why
won't.
am I stressing? Because it is this table that tells me whether I should be actually doing the estimate.
Mhm.
Because this table doesn't give routes with this method, then I should dump the method.
You should go.
I should dump the method. If it doesn't compare well, nicely with the Monte Carlo, then
No, but this is this COS method is more accurate. What is not accurate is the Monte Carlo. That is what should be improved. I mean,
Monte Carlo will be accurate because it's the standard here,
Mm.
which is the MC prices are the reference prices. The cost is what you are proposing is what you want to improve faster. So the reference prices here will be the MC prices.
Okay. Yeah, I can do that. I can do that as well. Yeah.
Any other questions?
If you say you know the characteristic function, what is it?
The characteristic function.
Yeah.
So you can start from the. We know there's the evolution of the asset price is governed by stochastic differential equation. So people can calculate the characteristic functions for that without calculating the the density function for that.
If you have a characteristic function, you can take your equation.
Yeah. Yes.
Get the density.
Then you have the next.
Yeah. So sometimes you can just calculate the characteristic without being able to calculate the density itself. Yeah.
And those AKs that you calculate at some stage, still have the density. You know, I remember.
Can you just go quicker?
Yeah.
So there's the AKs. No, the AK.
Yeah.
So they, in a sense, just the inversion.
Yes.
Okay.
Yes.
Why the cost approximation?
The
Why the cost approximation? Other approximations also.
the cost approximation. I don't remember the. Okay, I think that's a good point. Okay, but the COS method actually does lead you into using by using the Euler identity. You do eventually get to use the characteristic function, which is what you have. So instead, we don't use it directly because you can see that in the final formula that we derive, we end up having this. So the cosines are gone. All you have now is the characteristic function. So maybe you can achieve this in another way, but the characteristic function is what you have. So we are good once we get here.
When you go to your area table, did you investigate how the prices when you set your area too higher,
Mhm.
when you set your area too next to your initial underline to see whether the prices change?
Oh yes. So actually, the higher the barrier, the prices should increase, right? Uh, we can see this because if my barrier is closer to the, you can see this intuitive. If the barrier is close to the initial price, here, let me go back to my barrier here. You see, if the barrier and this initial price are very close to each other, then the chances of hitting the barrier are very high, which means whatever I'm trying to evaluate it at maturity is going to be weightless. So I'm just increasing the probability of not reaching or of making this weightless, the price. So we do expect that. However, the price at the end will also depend on the, or actually it depends on this difference between the, because you see I was varying my S, just my initial S. The closer it is to the barrier, then the weightless is the price. Then the further away the barrier from the initial price, then that one is more valuable.
Can you go to your cost method?
Which one? This one?
Yeah, yeah. So that means this can only be, this method can only be applicable for discrete monetary barrier. Is there a way you can improve that so that you can be able to price a continuously monetary barrier option also using the cost method?
What I've seen in the literature is that if you want to move from continuous monitoring, there's a way they improve I think they change the barrier by a certain factor so that they can be able to use their continuous methods in the discrete case. But in this case, because we discretize the times, and what we are doing basically is like we're evaluating European options in between the time intervals all the way to the initial time. So I don't know if by making these steps smaller will give you the continuous, but that can be compared once we have the continuous case results, and then we
I think for a postdoc it would be interesting to look at how you can um, improve the cost methods to be able to be applicable for continuously monitored barrier options. You'll see that in the paper by Chiarera and others in 2012, they didn't price the barrier option on continuously because they have never implemented something like that. So I think for a proper research, it would be nice to look at, spend time to look at how we can improve this methodology in order to cater for continuously monitored. I mean, I've also didn't see, I didn't see it anywhere.
yeah.
Yeah.
Okay, yeah, that would be interesting, I think, to look at.
No question. Thanks for coming.
Okay, okay, thanks, guys.
Thank you.
Thank you, Prof.